Hi, everybody. I'll be talking about the zonal winds compared on the night side and the day side, and the Venus Express data compared to the. Okay, so we've been talking about radio occultation a lot today, but it's I'm using the temperature and the pressure profiles that were obtained as a function of altitude due to the response to the local gradient of the refractive index of the atmosphere. So using these profiles and using the cyclostrophic balance, which is the balance between the poleward pressure gradient force and the centrifugal force, you can solve this force balance for the zonal winds. And this relies on the slope of the geopotential height surface at a constant pressure surface and the latitude. So in previous studies, this is Piccioli 2012, the zonal winds were retrieved from the Venus Express radio science dataset. And key things that are visible in here is the zonal jet that is at the cloud top at mid latitudes. And these were calculated by these geopotential height slopes at constant pressure surfaces. So by taking several pressure surfaces and calculating the slope of those, she was able to resolve these wind speeds. Now, they are an overestimation of the wind speeds as we compare it to in situ data for several reasons, mostly because of the assumptions in the cyclostrophic balance. Zonal flow, there it is. So the goals of this study were to reproduce the results of Piccioli 2012 and to use these methods on the Akatsuki data set. To observe the zonal atmospheric circulation and to test the stability of the mesosphere and the upper troposphere. And then we wanted to analyze if there is a diurnal variation of the zonal circulation. So using the two data sets from Venus Express and Venus Climate Orbiter, they have slightly different orbit characteristics. They had different operational times. So the Venus Express mission was from 2005 to 2015, and the data from the Venus Climate Orbiter is from 2016 onwards. So these are all the profiles that we used, and to prepare this data set for the cyclostrophic balance, we interpolated it on a logarithmically spaced pressure grid. And you can see it compared to the Venus Express, the Venus Climate Orbiter has poor latitudinal resolution near the poles. So with the geopotential height surface at a constant pressure, you can see that all the data points are within 2 standard deviations. We assume that there is no meridional circulation, no turbulent flow, and this leads to overestimation of wind speeds because both of these things will decelerate the zonal flow. And to fit the data, we used a cubic spline and took the slope of this to put into this equation. So some key differences between the Venus Climate Orbiter and the Venus Express. We used a Mann-Whitney U-rank test to test the significance of the anomaly between these two data sets. We found that there is a significant decrease in the zonal mean zonal wind speed. We're looking at the zonal mean, and it's actually a global mean with respect to pressure on the vertical axis, and you have wind speed on the x-axis. So the Venus Climate Orbiter is significantly decreased in wind speed compared to the Venus Express data set. And the mean temperature profile was not significantly different, but when you look at the upper atmosphere, there is a significant increase in temperature, and near the lower mesosphere and the upper troposphere, there is a significant decrease. And then we did this with the day side and the night side on the Akatsuki data. There was a decrease in the night side winds compared to the day side winds at the cloud top in the mesosphere, but they weren't really significantly any different in the lower end of the data. And there was an insignificant change in temperature. So bringing back the previously published results, we used different methods of smoothing the data. They took 5-degree latitude bins and smoothed the data over a couple of rounds. And we instead used a cubic spline. So we would have a difference in slopes, which would lead to slightly faster winds if there was a higher slope. So my results compared to the previously published, you can see that my magnitude of wind speeds are higher, but we have the same general structure. So there's the same zonal jet at mid latitudes, and we have decreasing speeds with increasing latitude. We also have the wind speeds at lower altitudes are much lower than the speeds which reach a maximum at this zonal jet right here. So my methods comparing VEX data to VCO data, we have the zonal jet here, which is around the same, approximately the same magnitude, around the same latitude, but it's in a slightly different position. So this is more towards the equator and this is shifted slightly poleward. And then comparing the day side to the night side, the zonal jet decreases in magnitude and it also shifts downwards and polewards on the night side. We looked at the static stability, which is the difference between the dry adiabatic lapse rate and the environmental lapse rate. And there is a slightly convective layer around 50 to 60 kilometers. It's near neutral, and then there's high stability in below this layer and above this layer. But this layer of near neutral stability shifts slightly downwards in the VCO data versus the VEX data. And then on the day side and the night side, you can see that this band here, it's much narrower on the day side than it is on the night side, and it is shifted slightly downwards on the night side as well. Next, we looked at vertical wind shear. What I was looking for with this is to see if the vertical wind shear was affecting the convective instabilities that would possibly be occurring in the near neutral stability layer. But the peak in vertical wind shear is above the near neutral stability layer at above 60 kilometers. And on the day side to the night side, there is more vertical wind shear on the day side than there is on the night side. So we have determined that the zonal jet that is at the cloud top at mid latitudes appears in all scenarios on the day side, the night side, in both data sets. At high latitude, the wind speed decreases with increasing latitudes. And the wind speed increases with decreasing pressure until about 1,000 pascals and then decreases. And the zonal jet shifts downwards and polewards on the night side. And these results agree with Picciali 2012 because the structure closely matches, even though our magnitude of wind speeds are higher, likely due to the different methods of smoothing. And there are certain limitations associated with these methods. The validity of the cyclostrophic balance is tested at the equator and the pole because of the geometry of the problem. Near the equator, you have the centrifugal force effectively reducing the force of gravity, and then near the pole, you get an infinity with the 1/tan of the latitude. The cyclostrophic balance also breaks down where there's a positive poleward gradient of geopotential height at a constant pressure. And the sample size, the latitudinal sampling, we had to combine the north and south hemispheres to improve the sampling. And the day side and the night side means are much sparser because we're using about half the data for each of them. Thank you very much.